find me and take one with me later on. I'm happy to, tweet or share on Vkontakte or whatever. I think it's no longer called Vkontakte, it's now called VK, right? Because everything's cooler now. Anyway, so this talk's going to be in English, but being in Russian, I'd like to, get out my old, really, really bad Russian skills. It's like the best sentence to learn in every language is to say that you don't speak the language, because it confuses the hell out of people. So it's like, я не говорю по-русски, извините. And they go, right? Anyway, доброе утро, Новосибирск. Как дела? Хорошо? Очень хорошо. Конечно. К сожалению, утром добрым не бывает, да? Хорошо. The rest is going to be in English, though. Anyway, so that was like 90% of my Russian. I think I can say like я хочу спать and я могу, но не хочу and all that kind of stuff. Like, the important bits. So I'm from Zurich, Switzerland, and I'm a very serious person. This is my LinkedIn profile picture. And it is really handy because it keeps recruiters away. So I am head of engineering at a small company called Archeologic. We basically try to help you do web VR and 3D on the web and AR on the web a little easier. So if you go to 3d.io, you find a bunch of libraries and APIs and components. Ask me about it if you're interested in that kind of stuff, and definitely give it a play. I'm also a Google developer expert, which is kind of why I'm here, for web technologies and Polymer. I'm also working with the Mozilla community, so I'm a Mozilla volunteer, a Mozillian as they call themselves, and I'm working with the W3C to give us web standards that actually make sense. And I highly recommend you to chime in. All the W3C standards and standard proposals are on GitHub, so you can open issues and you can make pull requests and you can make the web better. And that's kind of cool. As I said, I work for Archeologic, and we do have like a 3D editor in the browser, and we have 3D.io that makes it a little easier for you to do cool stuff. But whatever, today it's not going to be about 3D. Well, not that much about 3D. No, we're not going to do 3D, but we're going to do 2D. We're going to figure out how the browser actually does all this kind of stuff. Because when we start, we're not really getting like an image, right? We're not downloading an image, even though that for some websites would be smaller, which is a problem. So we're going to look at how how generally computers paint things onto screens, how compositing works. Then we're going to look at a real-world example, a very small one though, and then I'm going to have a quiz. Dun dun dun. You can win nothing, but nonetheless, you win eternal fame, I guess. I don't know. And then we're going to quickly look at WebGL and Canvas 2D as kind of like a bonus material round. I'm not sure if I have enough time for that though. So let's start with trees. This is a computer science thing, so trees, which for some reason, because this is computer science and not biology, our trees usually have their root on the top and then, grow to the bottom, as they do in real world as well. And we start not really with a tree, right? This is not a tree, or at least it doesn't look like one. This is a bunch of text. But what the browser does when it sees this is it starts creating a tree. And the cool thing is it does that as the data arrives. So we do not have to wait until all this has downloaded. I mean, this is not that much. I mean, unless you're on a Chinese mobile phone connection, which has like 0.5 kilobytes per second, you should actually get that really quickly. But if it's longer and more complex and there's like lots of images and stuff in there, the cool thing is that the parsing starts the moment it sees something that it knows. And the browser knows HTML, so it goes, ooh, this is an HTML document. This is not an image or a video. This is an HTML document. So I'm going to create a document node, which is our root node for the tree. And then we create a body node as that comes in. And then there's a headline with some text, so I create these as well. And you might want to change the text independently of the headline, or maybe you want to change the headline type to something else later on, but keep like the text, so that's why it's two separate nodes. And then we have an image, and we have to download that, yada, yada, yada. And what we have just created is the DOM tree. Okay, fair enough, that's relatively simple. I'm just ramping you up, it's early in the morning, strap in, and it's going to get more interesting. So basically we are parsing things as they come in, and we do the same thing for CSS. We're not creating a DOM tree for CSS, we are creating the CSS object model. So we have two trees that describe the content. But it is not really what we are seeing on screen, but it brings us one step closer, because now we know the structure of the things that we're going to see on screen later on. But we still have no idea how that's going to look. And also, how a website looks depends on how large the screen is and how long the text is and all that kind of stuff. The tree itself this tree does not tell us how long the text is or what color it is. There's another tree that tells us what the color is, but we don't know how much space we need for this. We don't know how much space on screen we need for this. So there is something else going on, and that's called layout or reflow, depending on which browser engine you're looking at. Gecko, which is the engine for Firefox, calls this reflow. As far as I'm aware, everyone else calls it layout, but okay. And it goes through the trees and figures out, okay, so how large is everything? So it basically makes calls to the operating system APIs and says, I have this bunch of text. How large on screen will that be if I render it with this style information? So it looks where to put things as well. So now we have this block level element, we have this headline, and then we have an image. Looking at the CSSOM, is that image like super large or is it very small? And maybe the headline is not a block level element, maybe it only spans half of the page, and then I can put, it basically moves boxes around. And it does that by looking at the two trees that we created. So it can only kick in once we have parsed the trees together. And it looks more or less like this. So here, as things are appearing in the tree, it figures out where they shall go, right? And it does that so it has to ask like, okay, how large is this text? How large is that text? There's an image, yada, yada, yada. And then it builds up this page. But I'm not sure about you, but when I browse, my websites look slightly different than that, right? Because, it's not just boxes. I have no idea. This could be any website really, and I wouldn't know because it looks like random bunch of boxes. So we have to do another step. Now that we know where everything goes and how much space it takes up, we can start painting. And painting is the process of actually filling in each of the pixels on the screen so that we finally get something more than the boxes. So now we have to paint in the boxes with actual text and images and all that kind of stuff. And how does that work? Well, really quick recap here. We have a high resolution screen of 3 by 3 pixels. Each of these pixels is represented by 3 numbers, red, green, and blue. And depending on how large the number is, the brighter the different tiny subpixels, the different tiny lights are shining and giving us different colors. Now, this is nice for us to understand, so I can easily map this square to this. Actually, this is not a square. This rectangle to this rectangle. But the computer doesn't really care if it's human readable or not. So the computer might as well just store it as a list. And that's good, because we know lists. I think, who here has worked with JavaScript arrays? I'm very surprised that some people are not raising their hands. Must be jQuery then. That's probably a jQuery plugin for arrays or something like that. So that means, I don't know, that's a really good question, but jQuery dot array probably exists and does something stupid like, I don't know, reshuffles the array or something. So the screen is basically just a list of numbers. And that's cool because basically that means when we know 3 numbers, we can make a pixel appear on screen. Okay, fair enough. And when we do that a lot of times, then we are rendering. So rendering is nothing special. It's basically just putting numbers in an array. Ooh, very complicated process. And when we figure that one out, then we can just go like, yeah, I understand rendering. And it took me far too long to make that GIF. Appreciate that GIF a little. Okay, thank you very much. Yeah, woo! I should print pictures of this, and I don't know. So basically, when we are painting, we are creating more or less rectangular boxes of pixels, or lists of numbers, really. And these lists of numbers are then called image, texture, or layer, depending on who you ask. Normal people would call them images. Graphics people will call them textures. Browser people like to call them layers. When you hear me say one of these 3 terms, they mean the same, really. There's a few intricacies of how these things actually map to real things, but for our purposes in this talk, they're the same thing. All right, and I'm not gonna just put one image there, I'm gonna put multiple images there. And this process is called composition. So basically I have multiple images and I put them in front of each other on the screen by overriding the numbers that I put in the list. Okay, fair enough. So for instance, here we have 2 colors and here's a 4th number. oh my God, he said 3 numbers, but there's a 4th number. What's going on here? The 4th number is the transparency. So how transparent or non-transparent a pixel is. Unfortunately, I can't really make the physical screen transparent, so I can't say like transparency 0 and then this wall magically disappears and turns into a glass pane, right? So instead, what we're doing is we have to kind of calculate how much these 3 numbers and these 3 numbers are combining into the 3 numbers that we're going to put on screen. And then depending on that, we get different colors. And we can use that for processes where we need, for instance, animation. So assume that we have a background picture and a Nyan cat picture. And I mean, it's a rectangle, but there's a bunch of pixels here are just like being ignored because their transparency value is 0. And what I can then do is I can basically start with putting the background in and then overriding it with the Nyan cat at some position. And then I do it again with a different position. And then I do it again and again, and then I have a Nyan cat. So this is how animations and rendering, hopefully at 60 frames per second or faster, is going to work. So basically we just write numbers from one rectangular area, from one image, and then we write other numbers from another image on top of them. That's compositing. And if I do that all the time, then I'm kind of good. And the cool thing is, unlike painting, where I have to put every pixel in, these copy operations are relatively fast because they are usually running on the GPU. But how does that actually work? So when you say like it runs on the GPU and all that kind of stuff, like how do we combine these numbers? And is there like more interesting ways to combine these numbers? In fact, there is, because there's a whole pipeline behind it. This is the rendering pipeline, and this is like a very simplified, very simplified version. It's dramatically oversimplified. I have a bunch of images, for instance, the Nyan cat and the background, and then I run them through a shader, and then I get something on the screen. What the hell is a shader? Who here has heard the term before? Very good. Have a coffee. So let's have a look at the GPUs and CPUs again before we go into shaders. So there's 2 kinds of processors in a computer or a phone, really. And one is the CPU and one is the GPU. I have made these like different personalities. This is kind of like a normal, sane person, actually, and this is like me with like lots of heads in one physical head. And obviously, in real world these days, the CPU can have multiple cores as well. They can do multiple things at the same time, like they have 4 or 8 or 16 or 32 or whatever cores, depending on a little bit of how much money you spend on your computer. Even phones have like 8 cores now, I think. So that's that. And then the GPU, this is like a very small portion of how many cores GPUs have. So basically, GPUs can execute a few thousand operations at the same time, whereas computers really physically can only execute 16 operations at the same time if you have 16 cores, or 4 if you have 4 cores, and so on and so forth. So thinking about that, you probably go like, why do we even do this then? Like, if this can do 1 thing at a time and this thing over here can do 16 things at a time, then this is obviously better, right? I mean, why would I want that then? I mean, come on. And the reason for that is that we have different kinds of problems. So normally computers or CPUs execute things that are very hard to do in parallel, right? So for instance, you might read from some memory, check what kind of value you got back, and then write to some memory based on that. And maybe you write back on the same spot in the memory, and then you read again, and then you kind of like, and there's a bit of a problem, because if you read and write at the same spot, so if I have like a little piece of paper and I write a number down, and then someone else comes and reads that number and goes off and does something based on that number, then we are kind of good. But what happens if we are both coming at the same time and trying to write a number on the same piece of paper at the same spot? It's not going to look good, right? Or if we erase things, then I might erase the work that someone else has just done. So we can't really do that in parallel. We kind of have to do that sequentially. So the computer is really optimized, the CPU is really optimized for that. It is really good at doing things sequentially and doing lots of memory access, and it kind of like predicts where it might go. So it tries to predict if it's going to jump into this part here or if it's going to skip it, and so on and so forth. So it optimizes these very complicated problems. These little fellas here are not very good at that, because they're like, this is far too complex for me. I'm a simple person. leave me alone. So they are like super overwhelmed as this kind of work. So they can't really do like concurrency checking and threading and all that kind of stuff. They don't know any of that. So all of these, each of them is simpler than this one. So this one can do really complex things as in general purpose programs, which they just can't. The GPU is just not capable of doing that. However, there are other problems where the problem itself isn't that complicated, and it can be parallelized. So here, this matrix multiplication, you know how it works, right? You take a value from here, take a value from here, and then you do basically the same thing with just multiple values. This is called single instruction, multiple data. And the CPU is really bad at that because it doesn't know about this kind of problems. So they're like, okay, so I take this value, calculate, 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 and put it out. And then I take the next value, calculate, calculate, and it takes a while, right? Versus the GPU goes, oh, right. Okay, everybody, grab a value, do the thing, next. There's no such thing as, oh, I'm going to read from here, and then from here, and then I'm going to write back here, and then I'm going to take this value and this value. It doesn't happen, right? So these kind of dependencies don't exist, so that's why they can do it in parallel, and they can do it really, really quickly. So they are excelling at this kind of problem. So these two architectures are solving two different problems. And let's think back about the screen for a second. This and this and this, that's lists of values. The screen is also a list of values. And we want to draw a lot of, or save or write a lot of values into these lists. So I would say this architecture is perfect for that. Let's have a look at how that works. So here we have an empty screen of 4x4 pixels, which conveniently is the number of cores we've got. But you get the idea. If we would have twice as many, we would still just do it in two runs through these 16 cores in the middle. And now we give them a task, and we say, hey, if I give you the x and y position on the screen, so we start at 0 here and go down to 3 here on both the x-axis and the y-axis. And each of them is just given their x and y. So this like 0, 0 goes to this one, 1, 0 goes to this one, and so on and so forth until we have 3, 3, which goes to this one. And they all do it at the same time, and they execute this little function here, where they just give us 3 values, x multiplied by, also the x coordinate multiplied by 85, y multiplied by 85, and 0. And they run that in one go, and voila, we have colors on screen. Cool. And this little thing down here, that's called a shader. That's what it is. So, quick recap, compositing combines images. And it does so by taking the images and running them through shaders. And shaders are basically just functions that run on the GPU. Or programs, if you want to call them programs, if that makes you more happy. So basically we have a function that gets a bunch of data, runs on all the cores in the GPU, and then produces values that we can put on screen. And the cool thing is, these shaders do not magically fall from a shader tree. We actually get to write these shaders, but browsers and other software comes with shaders built in so that we do not have to write them ourselves, but we can. And when it comes to shaders built in, if you have ever heard of CSS blend modes, that's just different shader programs that run on our different layers. So here we have 16 different modes. That's what the CSS spec currently allows. I think this is just like normal overriding. This is probably multiply. This is probably overlay or screen. So it's just different calculations. We have seen the calculation where we just multiplied the x and y coordinates by 85. They're a little more complicated than that, but basically that's what they do. They take 2 colors or multiple colors, transform them with a calculation of some sort, and then produce a color value as the output. Okay, what can we do with compositing? Well, we can change where we are writing to, and that means we can move things around. So we can translate, as it's called in computer graphics. We can also rotate, because rotation turns out to just be a multiplication with a matrix, with a rotation matrix. Nice. We can scale, because that's just multiplying the pixel values with a scalar value, for instance 0.5 or 2 or 10 or whatever, or minus 42. And we can do things like blend and filter, and that's just like, this is picking a different shader than the normal shader to actually produce these color values. However, blending and filtering are sometimes not supported on browsers. Certain browsers, they shall go unnamed, Firefox and Edge and Safari. So they don't support doing this in composition, so they're not having the shaders there. So what they're doing instead is they're actually painting all the pixels again, which is slower because we have to paint all the pixels in again versus just run them through the shader. And this is how a real shader looks like. You might notice it's not JavaScript. You might notice there are semicolons, and there have to be semicolons. This is because it's a language called GL-Slang or GLSL in this case. There's other shader languages as well, HLSL for DirectX, for instance. And let's go through this real quick. So we have a bunch of variables as our input. They have types. So this is a x, y. So it's an array with two things. It's an x, y coordinate. This is the data from an image. Okay, fair enough. Then we take that image, we take the color at the given position. So we're taking one color at a given position out of this. We are adding the red, green, blue values and divide by 3, which gives us one value. If it's a white pixel, that's going to be 255. If it's a black pixel, that's going to be 0. And every color in between is going to be some value in between these two. And then as the output, we are just taking this value for red, green, and blue, and that means that we are transforming the color. Who has an idea of what kind of color this produces? Or what kind of colors this produces? What does this thing do? It's a grayscale shader. So then you would basically run this program to create that effect. However, speaking of SVG filters, I think the Russian word for that is opazno or something like that, right? Is it? Opazno. Opazna, that's the thing. Я не знаю. Я плохо говорю по-русски, извините. So this is a CSS filter, blur. And I have enabled paint rect flashing, which means if there are pixels being repainted instead of just running the shader, there would be a green rectangle around it. So there would be like green pixels on screen telling us that this has been repainted rather than just composited. And we don't want a green rectangle because that would mean that something somewhere had to do and like paint all the pixels again. And we don't want painting because it takes time. However, this is the SVG version of that. It's the same filter. Notice the difference. Let's see. Notice the difference? Yeah. There's this green rectangle of sadness. It's here. And someone said to me, oh, no. Don't worry. SVG filters and CSS filters are doing the exact same thing. No. Нет. Ёлки-палки. It's not doing the right thing. So what I would like to see is that browser vendors would fix that and do something for hardware acceleration. And if they do, I buy them beer, because that would be freaking awesome to have hardware accelerated SVG filters. Obscure random pop music reference. Moving swiftly on. So I promised you a real world example of this. Okay, fair enough. Off we go. Here we have a little app that has this draw menu kind of thing. I mean, it's a really shitty app. It's a very templatey kind of stuff, but you know, the draw animation, that's something that we've seen a lot of times. And it's pretty popular, even though usability tests have shown that this is not a good pattern, because users don't understand that there is some content coming in if they swipe, or, you know. But I think that's actually changing slowly, because we are seeing these kind of navigation patterns all over the place. So we have a draw navigation. Okay, how do we implement that? Well, okay, we have a bit of HTML, blah, no one cares. And we have a bit of CSS. So our drawer, our navigation drawer, is an aside element. And what we can do is we can position that absolute and then move it to the left by minus 200 pixels. It's 200 pixels wide, so it's going to move out of the screen and it's not going to be visible. Okay, and because it's absolutely positioned, it's not going to cause an overflow. Okay, great. And then we have a transition down here, and we say when we change the left property for 1.2 seconds, which is pretty slow, just to make it very visible here, ease it in, and basically that's where the animation comes from. And then when we want to show that, if you like press a button or swipe or something like that. We're just gonna set an active class on the element and then set left to 0. Okay, so how does that do in terms of performance? So this is the exact example taken from the timeline. And here you see the frames per second, and here you see what the browser does in terms of work. Well, if I'm looking at that, so 60 frames per second is probably like somewhere here. We're having a few significant drops, and the browser is freaking busy. And there's a lot of green. And the green does reflect the green rectangle of sadness, so a lot of painting is happening here. All right, so let's have a look at that. Oh, wow, right? This is paint rect flashing. So every time it changes color, it has been painted, right? So it paints a few times. Yeah, maybe like, I would say it's safe to say more than 3 times, right? Or how I call it, this thing here, I call that the repaint disco. And it's fun to look at in the DevTools, but it's not really fun to do that on a phone, especially not on an older phone or an older computer. So let's have a look at the rendering pipeline again. This is the actual rendering pipeline. So we run some JavaScript, we change the class. Then the style changes because of that. So we say like JavaScript class list add active or toggle active. The style tree changes, so it goes into the DOM. The CSS or M tree changes the attribute. Maybe does a layout, then maybe does a paint, then maybe does a composite. Well, it is absolutely positioned. It's not going to move things around on screen, so we can skip the layout step. But we are still doing the paint step, and paint is pretty painful. Very good pun, I'm really proud of that one. And so I asked myself, can we do better? Yeah, we can. Very good. Yes! So here we're having the kind of like the same code, but here and this time I do a translate, right? And in the transition we then change the transform to get the translate in, and yeah, that looks better. That looks much better. Repaint disco is gone, and if we look at the timeline, smoothly sailing at 60 frames per second, and no work happens here. Yes, we did it. And that is really good, because if there's no work to be done, then it's inherently faster, right? And you know, that was where we came from. And I think when I look at the void of nothing here and the big chunk of work here, we have improved a lot. And that's pretty cool, because we entirely skipped this expensive paint step entirely. So that's pretty cool. And that's usually the rule of thumb. If you want to improve performance, try to not do things. That's not something that you should necessarily tell your boss. I'm not doing anything because I'm trying to improve performance. But actually, if you avoid work in the browser, that means that the browser has more time for other things, and we get better performance out of this. Paul Lewis famously said that. Unfortunately, left the Chrome DevRel team recently. All right, cool. Quiz time. I think I might have Swiss chocolate somewhere, not here, but maybe in the speaker's room I have Swiss chocolate. I have to check, I'm not sure. Anyway, so here we have an element. And we set translate x0, and after 2 seconds, we are setting it to translate x 200 pixels. So we are moving this thing to the right. And my question to you is, will it paint? No? Yes? Who here thinks no? Everyone's like, oh shit, someone said yes. I'm not falling for this one. Okay, who here thinks no? And who here is Swiss and goes like, I'm neutral? Okay, let's have a look. Oh no! Oh shit. Oh crap. So it does paint. But wait, Martin. You said it's composite if we translate something. So why the hell does it not just composite? Why does it paint? No. I didn't lie to you, but the thing is, so, yeah, but no, okay, fair enough, but it's not inline styles. And I did not lie to you, but composite needs layers. And layers, unfortunately, are costly. So you have a separate bunch of memory that you have to reserve, and you have to like manage a longer list of images that you have to composite. So the browser does not make a layer for everything, because that would take a lot of memory. Imagine having like a page like Contactio or something that has a ton of elements, and then you make images out of everything, and nothing really moves around all the time. So you create a lot of memory overhead for nothing. So the browser goes, I would like to save on this overhead of managing all these images and all this memory overhead of storing all these images somewhere. So what am I gonna do? And it goes, I have a look at what we are doing with these elements, and then depending on what we are seeing, I'm gonna create a layer. And obvious candidates are canvas elements or video elements, because they are repainting all the time anyway, so I have to kind of like, do that repaint job somewhere anyway, and then composite it over. And 3D transforms, because they are probably doing something like perspective skewing or something like that, so complicated 3D motions, and then I kind of benefit from running it through a shader, so we do that as a layer, as an image. Keyframes animations as well, no matter what they do, as long as it's like a compositable thing, so moving, rotating, scaling, all that kind of stuff, that's also very convenient to put in an animation, and then I can put that into a different image, because the animation is going to run a lot of times, so it makes sense. Even if it's like a 0.3 second animation, it's still a lot of work. So, and then there's the will change property. The will change property does not mean that I'm going to create, or the browser is going to create a layer. It is a hint to the browser that it might make sense to do that, but the browser is in no way forced to make that happen. Okay, another round. Slightly different code this time. Slightly different code. Very slightly. Correct. Will it paint? No? Yes? Да, нет, наверное? Нет. Хорошо. Конечно. Doesn't, because it's a 3D transform. Okay, one more round. Slightly different code. No? Correct. No! Ha! I fooled at least one person in the audience. Like, yes, it's gonna repaint because it's a 2D transform. Ha ha! But it's in the keyframe animation. So deal with it. Okay, cool. Huzzah! I do have some time to go over WebGL and Canvas 2D. That's convenient. This image has nothing to do with that. I just found it a cute cactus, so I thought I'd put it on a, Anyway, so I have a little challenge for Canvas 2D and WebGL. Draw the same image multiple times at random positions and random sizes. So it's not like something super complicated. Just resize the image and put it on the canvas as often as you can. The code for that, minus some setup code in Canvas 2D, looks more or less like that. We have a loop that loops a number of times, picks a random position, picks a random size, and draws the image at these positions and size. Okay? And then we have WebGL, which you're not going to be able to read because it's a little more code. I left out a bunch of setup code, and this is the code. It's a bit more. So for those in the back, this is clearing the color buffer. This is setting the size and position. This is then compiling the shader program. This is putting the data in. This is putting the vertex data in. This is combining the data with the shader program. This is the actual drawing, and then we basically just do like and this is the actual loop. This is doing the loop where we change the variables and draw the image. And there's a bit of setup code as well, but fuck it. So I think it's safe to say, when it comes to code size and code simplicity or complexity, Canvas definitely wins here. So let's have a look at performance. Oh, all right. So the y-axis is how many frames per second we get. The x-axis is how many times we draw the image. So if I draw one image, I get smoothly sailing 60 frames per second, and that's pretty cool. But with 100, I get like 35 frames per second, 250, 20 frames per second, 500 is a slideshow. Okay, fair enough. How much difference can then be like WebGL? Because we wrote so much code, it's going to be so much slower. No, it isn't. it's going to look like this. So the orange bars is WebGL, and it goes like 1,000 images. I eat that for breakfast. So, but then there's a setting that you can enable, which is hardware accelerated canvas 2D. And hardware accelerated canvas 2D does give us a bit of a boost. So this is 10,000 images, and we get a relatively quick slideshow. Very good. The computer gets really hot at that as well, which is nice if you want to heat your flat, because I think Siberian winters are pretty cold. But besides that, once we go to like 25,000 images, we have like a more or less-ish smooth experience still with WebGL, but let's not talk about Canvas 2D. So I think the performance point goes to WebGL. Okay, fair enough. So we have a draw right now. Let's have another challenge. Find the edges in an image. Okay, it's a two-dimensional image. It's not a three-dimensional problem. So what we want to do is we want to take an image like this. This is the Frauenkirche in Dresden. If you ever go to Dresden, definitely visit the Frauenkirche. It was destroyed in World War II, rebuilt recently. And we want to have the edges of that. So every edge that we are seeing here shall be transformed into a white pixel. Everything else that is not an edge shall remain black. Okay, how do we do that? So on the canvas, we kind of have a little function that runs over all the pixels, and it applies the isEdge function here. And the isEdge function is basically looking at the pixels around and then doing a very simple operation on them. And then depending on if it's an edge or not, we make that pixel black or white. For WebGL, sorry, this is the outcome. Let's have a look at that. So I can use the slider here and click on the slider. You see that? Click. Right? It takes a while to actually respond, and it's approximately 2 seconds. So I click on the slider, click, 1, 2, So it's 2 seconds. And actually, because I'm not running this in a web worker or something, if I run this on the main thread, the entire browser window kind of stops responding. So if I have like something else, it's going to stop responding. And that's not very nice. But this is the kind of performance that we're looking at. So it takes 2 seconds to process that image on this MacBook. And if we look at the timeline, it's a bit small, but basically this block here, that's the JavaScript that transforms the image data. And whoops. Okay, whatever. That was not supposed to look like that. And here we have like, this is starting at 1.4 seconds and goes to like 3.2 seconds, approximately 2 seconds in time. And it blocks the main thread, so no other JavaScript can run, no event handlers can run, GIF animations, and all that kind of stuff. Everything stops for 2 seconds. That's not a nice user experience, because we know that users think something is instant if it's under 100 milliseconds. It is more or less connected to what I do if it's within a second, and everything else is basically losing touch between what we did and what's happening on screen. So that's not very good. So let's have a look at WebGL. So we write a shader for this, because we are processing images, right? So here's a shader that takes as input variables the threshold, which is where the slider is, the width, the height, and the actual texture coordinate on the image. And here's the image, and it runs over them and basically tests for its edge. If the edge is larger than the threshold, then it's a white color. If not, then it's a black color. That's not too bad. Sure. This magical isEdge function in both Canvas and WebGL look more or less the same. It's a bit tedious. I'm not going to put it on a slide. The code is somewhere online if you really want to look at it later. And now we look at the timeline. And we notice once the image is drawn, so this is drawing the image is quite large actually, then here it stops doing work on the main thread. And that's pretty cool, because then it starts working on the GPU, which is where we want this to work, because we know that the shaders are pretty good at this kind of stuff. And the performance speaks for itself, and my clicker has died. So that's pretty cool. Actually, did I skip oh, I forgot to put in the GIF, huh? Anyway, it is pretty instantaneous, trust me on that one. So, to sum up, Canvas is easier to write vanilla JavaScript with, but it's not that much of a difference, because there's really nice libraries for WebGL, such as Babylon 3.js or others that make this easier. GPU.js if you want to do calculations on it. Canvas does not, even if it's accelerated, does not give you access to shaders, so you can't write your own and you can't run that much on the GPU, whereas WebGL gives you this kind of powers. However, the WebGL performance is highly limited by what the hardware provides, but the Canvas is limited to begin with, so it's not really a disadvantage. So make everything WebGL? Please don't. Because, you know, if you want to have a UI primitive and accessible content, then you probably want to go for HTML and CSS. Because you have buttons that actually behave like buttons, you have sliders, you have all that kind of stuff. If you click on a thing, something can happen. This kind of stuff does not exist in WebGL. You do not have event handling. You would have to implement everything yourself. That's not very good. If you want to have like responsive images, then use SVG. SVG is really, really good for that. And it's like for icon fonts and all that kind of stuff. If you have very simple two-dimensional image representations, if you just want to plot an image, for instance, or have like someone draw pixels on somewhere, then use Canvas 2D for that. And if you have something more complicated, be it 2D or 3D, where shaders could give you a performance boost, definitely run with WebGL. It makes sense to do so. Thank you very much. The slides are already online. Websites 3D.io, you can find me on Twitter or on the conference today. I'm going to fly out tomorrow at some point, so maybe I'll be there in the morning tomorrow. But definitely if you want to talk to me, or if you want to take a 360-degree selfie with me, then just come to me, talk to me. I'm happy to be here. Thank you very much for your time. Have a great day. I think we have time for questions now, don't we?
Yeah, 8 minutes for questions.
8 minutes. We're precise.
Hello.
Hello.
My name is Artem, 2JS. Thank you. It was quite funny and really interesting. Could we come back to the example with the slide menu?
With yes. Okay. Oof. How's your day going? Having a good time? Yeah.
Yeah.
Very good. Very good. Oh, we're getting close. Yeah. Yeah.
Okay. So we just add translate today, and it's great.
Mm-hmm.
So how will change could help us in this situation?
Right. Will change actually allows us to do something that wouldn't be possible without it, at least in Chrome. The other browsers, I think, implement it, but I don't think that they value it that much. If I would say here, so this code plus a will change left would have the same effect as the 3D translation. Mm-hmm. It's going to behave the same way.
Only in Chrome.
As far as I'm aware, only in Chrome.
Could will change be helpful for us in other browsers, and in which examples?
It can be, if the other browsers implement their rendering pipeline accordingly. The problem really is that the rendering pipelines inside the browsers are different, depending on how they are doing the shader management and like the layer management and all that kind of stuff. So for instance, all of these problems will actually not happen in Servo, which is the experimental browser engine for Mozilla, because Servo makes GPU layers anyways. It's just very clever about it. So this would not make a difference, but it will change. In other browsers, once they would change their rendering pipeline to use shaders in cases where it makes sense, would actually have the same effect. So whenever you have something like filters that are changing, when you have left or right or top or bottom that changes, this kind of stuff then would actually help you with will change together. As long as it doesn't cause layouts. If you are having like a relative position and it shifts things around, then you're back in layout land.
Okay, thank you.
Next question.
All right.
Кто-нибудь еще что-нибудь хочет спросить? There is no question.
Very well. Спасибо. Oh, Jesus Christ. Did I talk that long? Oh, by the way, regarding the will change question, I have a bonus slide somewhere. Give me a second. Jesus Christ. This is the support chart for will change.